Welcome to Lecture 2 in C++ CSC 121. Today we're going to talk about some basic concepts and some computer organization ideas. So, C++ is a programming language used to build information systems. Basically, it provides instructions to computers to perform various tasks. Software we write controls hardware. Object-oriented programming is a style of programming that helps us produce programs that more accurately model the user's needs in the real world. The two latest versions of C++ are 11 and 14, and they are standardized, meaning there is a committee that actually determines what is C++ and what isn't. So, hardware and software. Computers can perform calculations and make logical decisions much faster than humans. Today's computers can perform billions of calculations in a second, probably trillions or quadrillions, and more than a human could ever perform in a lifetime. That's where their power lies. The computers process data under the control of a sequence of instructions called computer programs. These programs guide the computer through ordered logical actions, and those of us who write those actions are called programmers. Programs running on a computer are referred to as software. A methodology for developing programs and increasing productivity is called object-oriented programming, and although it's debatable as to whether it's the best, it is currently the prevalent approach to software development. So, computer hardware continued. A computer consists of various devices referred to as hardware. We've got the keyboard, screen, mouse, hard disks, memory, DVD drives, processing units, scanners, printers, etc. Computing costs are dropping dramatically due to developments of software and hardware. And now computers that used to fill a room, they are less powerful than the things you have on your cell phones in your pocket. In terms of advancing power, there's something called Moore's Law, created by the founder of Intel, which basically says every year to 18 months, the capacities of computers have approximately doubled, and the costs have gone down commensurately. So basically, we'll see in a year and a half from now, computers should be probably doubly as fast. Moore's Law is beginning to break down as we get smaller and smaller and approach the atomic level and see limits caused by quantum mechanics. It's a relative observation. It's not actually a law. The Moore's Law and related observations apply especially to the amount of memory computers have. We've increased it dramatically. When I started out, 640K was a lot of memory. Now my current computer has 64 gigabytes of RAM and untold amounts of hard drive. They need to hold more data for longer periods of time, and these make computers more capable, and then we have to come up with more advanced programming languages in order to implement stuff. Similar growth has occurred in the communications field. Costs for network bandwidth have come through the floor, and there is no other field where technology improves so quickly with costs dropping like they do. And it has changed the world. The internet, for example, has made this literally a different world. So, regardless of how they look, computers typically are divided into various logical pieces. There's the input unit. These are devices for receiving input. This includes the keyboard, mouse, touch screens, voice commands, scanning images and barcodes, reading from the hard drive, anywhere data can come in. On gaming systems, you have accelerometers. On phones, you have them too. Face ID, all sorts of things like that. Anything pulling information in. The output unit is how to get the stuff out the door. You got monitors, printers, sound, all sorts of things. Various personal assistant devices. Google Play, for example. They basically take information and they put it out the door in the appropriate format. Inside the computer, we also have a memory unit. This is a low-capacity memory warehouse. It's primary memory, or RAM, random access memory. It's the memory in the computer. It is where the computations are stored, and it is dynamic. You kill the power, it usually goes away. Little bit different in the case of phones and such. They use more static form of memory, but the idea is the same. The ALU is the heart of the computer, It performs calculations such as addition, subtraction. It also contains decision mechanisms, for example, comparing items, etc. The ALU is implemented as part of the CPU these days. The CPU is the overall controller of the entire computer. It tells the input unit when information should be read, tells the arithmetic logic unit what information should be used in calculations, and it tells the output unit what should be done. Now, many of today's computers, including your phones, have multiple cores. In other words, essentially multiple CPUs. Basically, it's multiple CPUs on a single chip. A dual-core processor has 2 CPUs, quad-core has 4, and so forth. Today's desktop computers can have, mine currently has 16, for example. Secondary storage unit, this is long-term capacity, high capacity storage. It tends to be slower. Hard drives are good examples, CD-ROMs, all sorts of things like that. Flash drives, anything that can store data. And you can get hard drives these days as big as 10 terabytes just for your personal computer. So, data hierarchy. Data items processed by a computer form a data hierarchy that becomes larger and more complex as we progress from bits to characters to fields. We start with a character turns into a field becomes part of a record, and a record becomes part of a file. The smallest unit of data is a bit. A bit is short for binary digit, and it can have a value of 0 or 1. This is the base unit on which all computing is performed. There is a new concept in quantum computing called a qubit, but we're not touching that here. Characters tend to be combinations of bits. It's really hard to work with bits. People prefer to work with decimal digits, symbols, etc. These are known as characters. The computer's character set is the set of all characters used to write programs and represent data. Computer character sets have to be ultimately represented by zeros and ones. Fields are groupings of characters. Field is a group of characters with a semantic meaning. Field consisting of uppercase and lowercase characters can be used to represent a name. A field of digits could be their age, all sorts of things like that. A record is several related fields, and they're combined together to be a record. A payroll system might have an employee record, including the employee ID, which is a number, a name, which is a string of characters, an address, also a string of characters, a pay rate, which is a number with a decimal point, year-to-date earnings, which is a decimal point, etc. A company might have many employees and a payroll record for each. A file is a group of related records. More generally, a file can contain arbitrary data, but often it is organized. Similarly with a database. It's not unusual for organizations to have many files, some containing trillions of characters of information. A database is a collection of data organized for easy and efficient access. The most popular data model is called a relational database. Data is stored in tables, and a table includes records and fields. Each row is a record, each column is a field. There is also a new trend called NoSQL databases, which are non-relational document databases. The amount of data being produced is ridiculously large. IBM says there's 2.5 quintillion bytes of data, 2.5 exabytes of data created daily. 90% of the world's data was created in the last 12 months, according to Salesforce. Big data applications deal with massive data. So here are the units we typically see. 1 kilobyte is actually 1,024 bytes. A megabyte is 1,024 kilobytes, and so forth. The interesting thing is that using the K prefix and the M prefix actually is not 1,000 in computers, it's 1,024. So, how do we program these things? Programmers write instructions in various programming languages. Some directly understandable by computers, and others requiring intermediate translation. There are 3 general types. There's machine languages, assembly languages, and high-level languages. A machine language is the direct language of the computer, and it's the only one the machine can actually understand, often called machine code. It's defined by the hardware. It generally consists of numbers, ultimately reduced to ones and zeros. It's really hard to program in straight machine language, especially on modern processors. An assembly language has English-like abbreviations to represent elementary operations. These form the basis of a very simple assembly language. Translator programs called assemblers were developed to convert early assembly language programs to machine language. High-level languages are languages where single statements could be written to accomplish simple tasks like equations and output and input. Translator programs called compilers convert high-level language programs into machine language. This allows you to use an English-like language or a mathematical-like language to express your program. Compiling a high-level language can take a considerable amount of time. There's also the concept of an interpreter. Interpreters were developed to execute languages without compiling them. They work well, but they are slower than compiled programs. Basically, think of it this way. A compiler is a guy who takes a text written in Spanish and converts the text to something written in English. An interpreter is somebody who stands between you and another person and converts the language on the fly. Scripting languages, such as Java, are often interpreters. Interpreters have an advantage over compilers in internet scripting because it can begin executing as soon as the client begins downloading. But the downside is interpreted scripts tend to run slower and consume more memory. So that covers our basic introduction, and from here we'll move on to learn more about the basics of